Um, so yeah, I've started the recording using another device. So it's my great pleasure to welcome today Youssef Allouah, who's doing his PhD at EPFL and who in security of machine learning in Byzantine machine learning. And today he's going to talk to us about a work we did, which is extremely relevant to Tournesol, which is, since it's the algorithm at the core of Tournesol, about robust pass voting. And without further ado, Youssef, you have the floor.
Okay, thank you, Lee. So, as I said, I'll be presenting our work on the problem of robust sparse voting. This is a joint work with Lee, Oscar, and Phil. So, as you all know, the problem of voting is really everywhere. You vote for which movie is the best. If you use Netflix and leave recommendations, you also vote for the president, usually, depending on your country. Machines also vote when they solve problems. Let's say if you're familiar with distributed computing, consensus, which is a fundamental primitive in distributed computing, can be seen as a voting problem. And of course, you can see machine learning systems as voting for applications such as ensembles and the likes. Okay, so of course it's important to have very good voting algorithms or robust algorithms and also fair algorithms, because we use these algorithms to actually make decisions. Um, and finally, it's a challenging problem. I'm referencing here a very well-known result in voting theory, that of Kenneth Arrow, which actually says that it is impossible to have just a couple of very desirable properties, very straightforward properties. Essentially impossible. So voting is not a straightforward problem, and people have been working on it for a very long time. We consider a certain flavor of the voting problem. So we're considering, let's say, on the left, the circles you see are voters, and on the right, what you see are what we will call alternatives. So, for example, in Tournesol, those are videos. They can be anything. They can be any alternatives. Okay. Um, and the situation we have is that voters go to some alternatives, not all, as you can see, and they give scores. Okay, in all generality, you can just imagine that scores are just some real numbers. Okay. Um, in voting theory, this is called cardinal voting, as opposed to the more classical ordinal voting. So people sometimes do not give scores, but they just say, I rank preferences in this way. So I prefer this movie over this one, etc. But you can always transform these into continuous scores, and actually continuous scores um, embed more information than, or
Youssef,
yeah. Yeah.
there's an issue with your slides. We only see the first slide right now.
Oh,
Um,
that's okay. That's a big issue.
can you redo the screen sharing maybe? Oh yeah, now it's working. Okay, it's all good.
Oh, okay. So I was in full screen mode, and maybe that's not working. So I'll just maybe stay in this um, window mode.
Yeah.
Yeah. So hopefully so far it's good. You were able to synchronize with the slides. Um, yeah. So essentially this is the general problem we're considering. Voters give real number scores to some alternatives, not all of them. Okay, this is obviously very realistic. Okay. Um, so the question we ask is, how do you aggregate discourse? Okay. this aggregate, the output of any aggregation mechanism that you will use is simply the voting outcome. Okay. Um, so now I'll be outlining three challenges that actually are what the together they make up the robust sparse voting problem. Okay. So the first challenge is sparsity. As I explained, voters do not score all subsets. As a matter of fact, the realistic scenario you could think of is that they score a very small subset of alternatives. Think of videos or the likes. On YouTube, for example, you will probably be watching a very small subset of YouTube videos and even scoring a smaller subset of these videos. The second challenge, that's actually one of the very important problems when you consider scores, all right, like numerical scores, real number values, is that of preference scaling. Now, to explain this, we can look at, for example, scientific peer reviewing. And there you will really see this idea that people may have the same preferences, but they will express them very differently if you ask them to report them numerically. Okay. So think now of alternatives as papers, and you have two reviewers. Okay. So reviewer one is the kind of enthusiastic, let's say, young researcher who, if they see a good paper, they really give it the strong accept. While reviewer two could be a more senior reviewer who uh, avoids giving, let's say, definitive or extreme decisions and would go for weaker uh, statements, and they would go for weak accepts. Okay, these kind of things. And if you think about it, reviewer one and two, they actually have the same preferences. They like the same papers, and they would reject the same papers. I'm not showing examples of rejects here, but those are just different styles of reporting preferences. But they ultimately believe that the same outcome should be um, should occur for all of these alternatives, all these papers, meaning that they should be accepted. Okay, hopefully this is clear. Um, a third challenge is that um, some of the voters may be strategic and they may be malicious in their behavior. Specifically, the threat model we'll be talking about is that of Byzantine. It simply means that some voters are arbitrarily malicious in the sense that they just indiscriminately want to hurt the outcome. They want to destroy it by any means possible. They don't want to see some specific outcome happen. They just want to ruin the algorithm as much as they can. And in thinking, in modeling these adversaries, we will not make assumptions about what they know. We'll just simply say that they can only give their own scores. That's all they can do. But they can, for example, look at other voters' scores. They know how the algorithm works and the likes. Okay. And if you let's say think of F as the number of voters, number of malicious voters that you have in your system, and that they let's say represent even less than 1%, okay, of voters in your system, it's actually leading to a false sense of security, in the sense that because we in realistic scenarios, as I said earlier, um, votes are sparse, meaning that a single alternative, if you think of the last one here, the last box on the right, it only has two voters who scored it, and one of them is a malicious one, and that's enough to be very bad for the outcome of the vote on this alternative. Okay, so it doesn't matter what fraction you have of malicious voters in your system. if you have a very large sparsity, and you should expect that very high sparsity will happen in real applications. Now, those three challenges on the problem I described are what make up the robust sparse voting problem. Now, we're going to think on the defender side. So if we're designing a voting algorithm, what are the properties that we want this algorithm to verify to say that it's an appropriate solution for robust sparse voting? And the first one we will call Lipschitz resilience. Okay. Now, what it simply is that we want no voter to have arbitrary influence on the system. We say that a voting algorithm is L Lipschitz resilience. You cannot move the global vote by more than L. Okay. So so formally speaking, so this is informal. Formally speaking, what you would want is that if you add a voter to the system, it cannot move any alternative score by more than L. Okay. Obviously, the smaller L, the better. Okay. I hope this is clear to everyone. You can stop me at this point if you want. Now, the second property that we will be seeking is what we call sparse unanimity. Okay, so unanimity on its own would be that if all voters are honest and they agree, then the vote should simply return this unanimous preferences. Okay, now we're talking about sparse unanimity because the challenge here is that they all agree, but they do not score all alternatives. Actually, they score different alternatives. And what could be worse is that the set of alternatives that they score are actually biased. They're not uniformly random. So it's really, if you think about it, it's a hard problem. It's challenging. So that people would not only score different alternatives, but if they express their preferences differently, as we said earlier, it's going to be hard to know that they actually agree. Okay, so you don't know that in advance, of course. So far, I've presented what the robust sparse voting problem is. I told you what are the properties that we're trying to achieve. Okay. Now we have one kind of security property, that's Lipschitz resilience, a very strong property. And we have a correctness property, sparse unanimity, and it's actually a pretty simple one, but you will see the problem is very challenging. And the formal argument we have for that, for example, is that we have some kind of impossibility result on sparse unanimity specifically. So the results essentially says that let's say, imagine, forget about your Lipschitz resilience for now. Imagine everyone is honest, okay, and they're not scoring the same alternatives, okay, so they have very different alternatives scored, but they have some intersection so that you can kind of compare the alternatives. Even then, if your only strategy is to go for each voter and normalize their scores without looking at other voters. So for example, you simply say, I'm going to go to each voter and I'm going to make sure that all their scores are between 0 and 1. Okay, so I will divide by the maximum score per voter, something like this. Okay, and this actually will not work, meaning you do this local normalization, you do any aggregation you want, any reasonable aggregation you want, you do averages, you do median, you do any kind of thing, you will not recover the unanimous preferences. Okay, so that simply, so what that suggests is that to kind of solve this preference scaling problem that makes sparse unanimity so challenging, you need to scale voter scores by looking at all the votes simultaneously. You cannot just take each voter separately and normalize their scores. that doesn't work. Okay, so we kind of want some collaborative preference scaling. Okay, and so this is what we do in our algorithm. I will explain it in more details in the next couple of slides. But essentially, this is one of the, I think this is the main feature of our algorithm. So what it does is that we kind of, for each voter you go and you try to look at what is their scale compared to some average scale that you have. Okay, and you try to put all the voters on some common scale. Once they are on a common scale, if you do it properly, then you can just simply use your favorite aggregation. And if this aggregation is robust, then you will, if you do things properly, then you will be able to get the two properties we mentioned, and so have an algorithm that's very good for robust possible, which is what we do. Okay, so this our algorithm is called Mehistan, and it verifies both of these properties. So now yeah, we have some formulas here, so I'll try to explain how Mehistan works without going into too much details. Just some couple of notation. I will, whenever we want to denote a voter, it's n, and alternatives is small a. Okay, and theta n is the score vector of voter n, and a subscript n here, sorry, subscript n is the set of alternatives scored by voter n. Okay. Um, so Mehistan works in 4 steps. Okay. So the first step is local normalization. Okay. So as I said, you can just go to each voter and put all the scores between 0 and 1. Okay. So for example, the way we do it here is we do min-max normalization. So you're sure that the smallest score is 0 for each voter, and the largest score for each voter is 1. And this is an affine transformation. So you preserve everything such as orders and also relative uh, uh, preference scales. Okay, so that's why we do this kind of transformation. It's because it's positive affine transformation. Okay, then the second step in my stand is to search for a scaling factor. Okay. Now I'm gonna do a fast forward here, and I'm gonna tell you what are we trying to look for at the very end of this algorithm. So we did our local normalization. We'll be looking for a scaling factor, call it Sn, and a translation factor, call it tau n, so that uh, when we transform the normalized score vectors, Sn plus tau n, we can just simply aggregate them using some specific alternative-wise aggregation, meaning we go to each alternative and we just use, for example, median or so. Okay, so this search of scaling and translation factors is just to put all the scores on the same scale, and since it's positive affine, as I said, it will preserve many good things such as order and the likes. Okay. Now go back. I'll go back now to how we perform this scaling and translation factors search. So first, for every pair of voters, N and M, we compute a comparative scaling factor. So it's a comparative scaling factor we call SNM. And what this is, it's an average ratio of score differences. Okay, so you go over all pairs that were commonly scored between N and M that are different. So these pairs can serve as anchors or points of references. So what we do is that we see how differently voter M scored A and B, and then we compare that to how how differently N scored A and B, and that tells us how different the scale of um, uh, um, voters N and M are. Okay, so we know what is kind of the difference between their scales that they are voting, that they are reporting their scores on. And once we know this, what we will simply do is that we will aggregate these 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 comparative scaling factors. Okay, and here instead, so this is our robust aggregation. Now, for now, I will not explain what it does, but if there were no malicious voters, here we should have simply taken an average. Okay, so for now, you can simply think of this as an average. Okay, so we average all of these comparative scaling factor, and it tells us, okay, this is your scale. Okay, so SM is kind of telling us this is the scale that voter N is kind of using. Okay. Now, when I move to the translation factor search, so it's very analogous to the scaling factor. So here, what we do is that, okay, we scale each voter's normalized scores. Okay, so now once we've done this scaling, they are now on the same multiplicative scale, if you would. Okay, now we got the kind of the slope, right? And we want to know the offset, kind of. So what we do is just we simply look at the average difference for commonly scored alternatives. Okay. Then those are comparative translation factors. Once again, we do the same thing. We aggregate this comparative translation factor, and we get a translation factor per voter. Okay. And then all we need to do is we need to do a transformation, an affine transformation, using the scaling factor that we found and the translation factor. Okay. And at the end, all we need to do, I think it's not showing up here, unfortunately. I missed an equation. But we just, again, use our aggregation to aggregate the scores along each alternative. It's very simple. Okay, so for example, you go across each alternative and you do an average of these theta n hats. Okay, these rescaled scores. Okay. So I think if hopefully this is all clear. You can once again stop me to ask questions. Now I thought I shouldn't go into more details because otherwise it would have taken so much time. But I'm going to tell you a bit about how this aggregation works. This so the LR mean stands for Lipschitz robust mean. Okay, and all it does simply is that it's trying to recover the average without letting any voter have a let's say an influence more than L/7. Remember Lipschitz resilience? This is the parameter here. So you give it L/7, and this is making sure that you get an average if there are enough voters, and that each one of them does not have more than L/7 influence. And the way we do it is that we compute a median, but a regularized median. So you can think of a median as an optimization problem where you try to minimize the sum of absolute values instead of the sum of squared values. What we do is that we add a regularization term that's scaled by the Lipschitz resilience constant that you want. And we show that this is actually enough to get our L-Lipschitz resilience guarantees in such a way that if you do each aggregation, as I mentioned, with a L-Lipschitz aggregation rule, then all in all the steps, they can be combined and you can show that your algorithm overall is L-Lipschitz resilience. Okay, hopefully this was clear. So you can find more details on a version of our paper on archive. And it's actually like Lynn said, the algorithm is used is adapted, I believe, to the use cases of nous sommes. Yeah, so that's the end. You can take questions if you have any.
Thank you, Youssef, for the talk. I think it was very, very well explained. Are there any questions? Yeah, Romain?
No, I just wanted to upload, but I click on the wrong button, so I don't have any question. Thank you for the presentation.
Thank you.
Okay, so if I may, one question: did you investigate some other methods than the one that you propose and discard them because they didn't have the properties you liked? If yes, can you tell us a bit about these other methods that you looked at?
Yeah, thank you, Louis. It's a good question. So if you think of the properties separately, we do explain that in the paper. So for example, the Lipschitz resilience property, we show that something like any weighted average cannot verify it, and it's that this is something that very natural, as you can imagine. So you want to go for something like a median, and even then we show that the median is actually it cannot be Lipschitz resilience. So you really need dedicated aggregation methods to be able to guarantee this kind of a parameterized resilience that you can control. So that's on the aggregation part. On the sparse unanimity property, so it's as I explained, like the very natural, I think, baseline you would think of is if everyone agrees, they're all honest, they just score some different sets of alternatives. The very natural thing is just to say, if they have different preference scalings, I will just renormalize the score vectors individually. But as we show, it doesn't work. Like so yeah. So those are like the baselines that we considered. Yeah.
Okay, but so my question was specifically about the manner in which you compute the scaling. Did you? So I guess there is a proof somewhere that the manner that you use fulfills the sparse unanimity property.
Yeah.
Okay, and did you investigate other methods for doing the scaling, for which maybe you were not able to prove that they fulfill? What was your this is quite complicated. It was probably not your first try at doing the scaling.
Yeah. So we tried something else. So I actually believe this is the simplest version, the most natural attempt that we had. It's the one that you see here. It's like computing ratios on the commonly scored alternatives and then just aggregating these comparative ratios. We've tried other things. Like I think one attempt I can mention is you can try to look for a couple, so a pair of alternatives that everyone scored. Now you can assume that there is a pair of alternatives. You can ask all your users, for example, in the system, to score some pair of alternatives, and then this is the pair that you want to use to actually put the votes on the same scale. Okay. And there you can do simpler operations similar to these, but only on this pair of alternatives. Now this works well for sparse unanimity, but you would lose Lipschitz resilience because the malicious voters can simply play with these distinguished alternatives.
Okay. Also, I think probably one of the challenge for this is when you study sparse unanimity, you consider everyone to be in agreement, so with the exact same preference. Am I correct? And I would guess that I would guess the main challenge is actually having disagreement and still being able to do the scaling in the context of disagreement.
Yeah, so that's actually a very good point. So as I kind of skimmed through the properties informally, I couldn't explain that. But what we mean by agreement is not equality in scores. What we mean by agreement, so you and I agree on our preferences if on the commonly scored alternative. My scores are a positive affine transformation of your scores.
Yeah, okay, that's also what I understand. But so on my side, I was part of the team in Toronto that implemented this in the system, and I was trying to think quickly about other methods that we could use for the scaling. And what I found very challenging is how do we do the scaling when actually there is not this pseudo equality of the preferences on the subset that to personality, and especially cases where the community prefers A to B, but some individual prefers B to A, and how do you compute the scaling for this individual plus a lot of other data? It was quite challenging.
Okay.
And is there any measurement of how good your scaling is after you have computed it?
Yeah, so we have some experiments on the paper. In the experiments, we had to have some kind of ground truth, obviously, to be able to say how good we are. And so we used synthetic data. And I'm not sure, like, for example, Tournesol, you can. I'm not certain how you can say how good some scaling operation is without having some kind of ground truth. Yeah.
Oh, okay. And so with synthetic data, you were able to find the parameters with which you generated the synthetic data. Is it with a perfect match or?
Is your question how we generate synthetic data, or how good are we on the synthetic data?
How good are you on the synthetic data?
Okay, it's pretty good, I would say. So what we measure is that, like, the measure we use is correlation. So, like, Pearson's correlation between the outcome of the vote and the ground truth that generates all the votes. Okay. So you kind of, what you do is that you take some score vector on all alternatives. Then you mask this vector differently for all voters. So you give them different subsets of this vector. And then you go at each voter and you rescale with some different, you do some random affine transformation. And then you do all of your algorithm, your voting algorithm. The output you get, you compute the Pearson's correlation of the output you get and the original score. And we were getting very good correlation values, as long as the sparsity, like kind of how often alternatives were how many alternatives there were per user was like something above, I think, 10 or 20%, if I'm not wrong.
Maybe also to clarify to the question of Louis, like even in the synthetic data, there was still a ground truth. Like it was like approximate sparse unanimity, like in the sense that like people deviated from a true preference, right? But it's not like you had really different preferences, like.
Yeah. Like, was this clear, Louis? Did I answer your question?
Yeah, it's full. Thank you.
Okay.
But yeah, as a follow-up to Louis' question, yeah, how would you weaken? I mean, we get issues with sparse unanimity condition, which some reviewers regarded as too restrictive. Like, what do you think would be a good relaxation of this assumption?
So I would say that I go back here. Yeah, I would say, like, if you look at this statement here, like the ways you could weaken it is saying that, well, instead of all voters are honest, you could say some voters are honest. So you can go for this approximate sparse unanimity. But if you I guess you want to detach it from resilience. If it's the case, then I guess the straightforward thing is to try to have the same property, but not all voters agree. So you have a majority of them that agrees, and then let's say there are two ground truths. So you have two groups, let's say, and you want to say that you recover the majority for these two groups, or some kind of weighted, some convex combination or something like this of these original preferences. I would also say that one other way to weaken it is probably to have a weaker definition of what equivalence of scores means. So right now what we do is a positive affine transformation, but you can simply say that two scores are equivalent if, for example, they have the same order, they induce the same order, sorry, from alternatives, and you can see if whether you can have some kind of ordinal sparse unanimity.
Yeah, some order preserving property.
Yeah. But like we obviously, I guess, tried the second one I mentioned, like trying to return what the majority agrees, and we just failed. It's like you can. I think it's not so hard to approximately return what the majority expresses as preferences, especially if you have a Lipschitz resilient algorithm. Because if you think about it, Lipschitz resilience tells you that you can ignore some of the voters, and up to L, up to some big O of L, you will get the right preferences. And if the voters you want to ignore is simply the minority, and then you can use our existing results, but up to some errors, and we can have some kind of approximate sparse majoritarianism, if that's the correct way to say it.
Yeah, like as a corollary of a proof, you can derive the fact that you have some quasi-sparse unanimity. I think like the correlation might go down in maybe F over L, if F is the number of malicious guys. Oh, we don't derive it, but
Yeah,
something like this.
yeah, makes sense.
Maybe a question that something that we discussed prior before that with Louis was the idea of aggregating comparisons rather than scores. Like we explored a bit the idea. Do you remember a bit why we gave this up?
Aggregating comparisons instead of scores. I'm not sure. Did we try this? I'm not sure. Did we try aggregating comparisons?
I mean, at one moment, we definitely had the thought that what if we try to aggregate comparisons and then have like aggregated comparisons and then build the scores out of this.
Oh, okay, okay. I see what you mean. Like we were talking about this. Was it through so you get comparisons, then you try to produce cardinal scores, and then
Yeah.
you go to okay. Um, I think the reason is that the correctness property was not as clear as here. I think what we tried to do is we tried to formulate it as a quasi-natural optimization problem, and but I think that it was hard to sorry, like the problem was not very regular, so we could not, I guess, solve it simply, or yeah, or it had different minima, so we were not sure about whether we got the right. As I said, the correctness as here, I think.
Yeah, the model was definitely less clean. Is there any other question? Yeah, I think otherwise we think we can end this here. Well, thank you very much, Youssef, for this talk. Thank you everyone for coming. We'll have another Tonsol talk in 2 weeks, and the speaker will be Martin Gibert, who's a philosopher, and he will be discussing the difference between a moral agent and a moral patient, and what it entails, what it implies for the case of AIs. Thank you all for coming, and hope to see you next time.